Hey, good morning, everybody. We're going to talk about intermolecular forces and some of the properties and things, and really talking about the different types of molecules that go along with that. So you picked up this handout in class today. This is sort of a cheat sheet of what we're going to look at, or sort of a cheat sheet you can use to help you determine like what's the major intermolecular force. We'll use this kind of at the end to kind of justify what types it is. But again, you can pause it or print this out. And again, sort of just a flow chart. Really, what we're going to be looking at are sort of our ions or molecules formed, and then are they polar or non-polar? But here we go. These are the different types of intermolecular forces that we have, right? Most people, if you have any background, know about dispersion and dipole and hydrogen. We'll talk about those in just a second. These are generally the new ones that people don't know as much about. In fact, ionic bonding, right, the attraction between two different charged ions, is an intermolecular force. So we'll talk about that in today's lesson, but just a little bit of information about that. So what are intermolecular forces, right? Intermolecular forces are really important in understanding why molecules or compounds behave the way they do. The way in which molecules interact with one another really depends upon the attractive forces, not only within the molecule and the bonds that form between them. We've been talking about that lately, but also how the molecules interact with one another. Some kind of phenomenon that we see that are explained by intermolecular forces include what state of matter is it at a particular temperature, what is the surface tension interactions between molecules, right? The phospholipid bilayers that we see in biology, some of the cell layers, and a lot of material sciences, why and how things are created to interact the way they do, really depend upon intermolecular forces in order to make them work. So let's talk about that. Here are some water molecules. Water is really, really important, not only for our sort of chemistry, but just our everyday life. Now, there's sort of a disconnect sometimes students have with like, well, what are intermolecular forces? What they're not are these. These are intramolecular forces. Intra is a prefix that means within. And so what I have highlighted here are the covalent bonds between the hydrogens and the oxygens, right? We've been talking previously about the nature of a bond, and this is a polar bond because of the difference in electronegativity between the oxygen and hydrogen. Again, that's not the theme of this unit. That is an intramolecular bond, a bond that forms between any two atoms. This unit is about intermolecular forces. Intermolecular forces are the interactions between different molecules. Usually, we kind of illustrate those with these sort of dashed lines, but more importantly, notice that they are not the bonds within the molecule. They are the sort of associations or the attractions between different molecules. Sometimes those molecules are the same, like we have here in this illustration. Sometimes those molecules or ions are different, and that's okay too. But most importantly, right, it has to do with the interactions between molecules. And again, that has to do with the polarity of the molecules, which we've discussed in our previous unit. Let's start with one type of intermolecular forces, which is called dipole-dipole interactions. Dipole-dipole is one of the sort of types of intermolecular force, but it only occurs with polar molecules. And you can maybe remember that when we talk about drawing the dipole, those represent sort of the arrows that show the sort of uneven distribution of the electrons around a molecule. We sort of draw dipole and dipole moments, the sigma positive and sigma negative. Well, we can only have those exist if we have polar molecules. Now, this kind of polarity, the reason that the dipole exists is the permanent uneven distribution of the electrons in a molecule. That has to do with this sort of difference in electronegativity. So we have two polar molecules here, hydrogen chloride or hydrochloric acid. And you can see that these are those sort of dipoles that I'm talking about. Those are permanent. Those are never going to go away because of the permanent difference in the electronegativities of the atoms of hydrogen compared to those of chlorine. Now, none of that is a dipole-dipole interaction. The dashed line between molecules is the intermolecular force. Because these are permanently polar molecules, we would categorize this type of bond as a dipole-dipole interaction, right? Notice too that intermolecular attraction happens when the positive end of one molecule is aligned or sort of next to the negative end of another molecule, right? So we would expect that this is sort of a form of attraction. And so these molecules would want to sort of stick together, as it were. Okay. Oops. Let me go back to that illustration. So here's sort of that interaction. We have a couple of permanent polar molecules here, these uneven sort of lobed kind of potato looking things that are molecules. And we see that they have opposite sides to them. Those positive and negatives never change. Now, when these molecules get close to one another, excuse me, you'll notice that the positive end of one molecule sort of is influenced and sort of attracted to the negative end of the other molecule. We refer to that as a intermolecular force and a dipole-dipole interaction. Okay. Now here's another similar one, but different. This is called an ion dipole force. Okay, so we don't have two dipoles, which means we don't have two polar molecules. Instead, we have an ion related or sort of connecting to a dipole. Now, where do we get ions from? Ions, remember, are atoms that have gained or lost electrons to create sort of these permanent negative or positive charges. We see ions form when we have ionic compounds. So to consider this crystalline lattice structure, this positive, negative, green, purple alternating crystal that we have here. We know that when we put sodium chloride in water, that this big chunk of sodium chloride sort of disappears. It breaks apart. Well, what enables that? Why does that happen? And why does it not always happen with all compounds? Well, it has to do with the polarity of molecules of water interacting with these positively and negatively charged ions. We've talked previously about how water is a polar molecule. The lone pairs of electrons around the oxygen make it polar. And there are these permanent dipole interactions that exist, okay? So positives around the hydrogens, negative around the oxygen, right? Because of the lone pair of electrons. Now, when we think about how these molecules interact, like why or how would these sort of water molecules arrange themselves around these sort of different positive and negatively charged parts of the salt crystal? And so here's kind of what it looks like at the end, right? About how water molecule has sort of pulled and separated these ions. So a couple of things. Notice that the sodium chloride is no longer in solid salt form. The ions have sort of been isolated and separated. So this is that aqueous, the AQ that we write when we write net ionic equations, right? They're no longer attached in solid form. They're sort of dissolved, swimming around in the solution. Something else I want you to notice is about how the water molecules orient themselves around the charges. Does water have the same orientation around all the positive charges as it does around the negative charges, right? If you'll notice that around the purple, there's the red side of oxygen closest to it. Well, what's the red side? If we go back, remember that that's where the lone pairs of electrons are, and that's negative. So why would the sort of negative side be closest to or sort of near the positively charged ions? Well, that's because there's an attraction between those molecules. It's how water sort of pulls the purple sodium ions away from that crystalline solid lattice. Take a look around the negative chlorine. What do you see is different? Notice that the white side of water molecule is aligned up around that. Well, what is the white side? Remember, that's the positive charges because hydrogen has a lower electronegativity and oxygen is pulling those sort of shared electrons away from it. So the positive side of the water molecule is sort of completely surrounding the negative ion, which is the chlorine ion, right? And so we call those solvation or sorry, hydration shells. And this is not by accident. This happens with any sort of charged ion. Again, this is an ion dipole, right? A polar molecule interaction. So these don't have a direct bond. These two things are not sharing the electrons, but these two molecules or ion and molecule are attracted to one another through these intermolecular forces. Okay. And so it's really important to kind of understand, right, how polar molecules will differently orient themselves around ions based on what the charge of the ion is. And so again, why aren't the positive sides next to the positive particle? Well, again, that because those like charges will repel. It's the same reason why the negative oxygens aren't facing the negative chlorines. Okay. So again, this is the ion dipole, right? An interaction between an ion and a polar molecule. Here's a third type, which is called hydrogen bonding. Hydrogen bonding is a specific type of dipole-dipole interactions, right? So again, it's between two polar molecules. In this case, we're still hanging out with water, but I sort of make up this joke that hydrogen bonding only happens when the molecule is having fun, right? Notice the sort of play fun. So this special bond, right, between different molecules, positive of one molecule and the negative of the other, can only exist between hydrogen, right? Hence why it's hydrogen bonding, and three other elements. Hydrogen's having fun, right? So hydrogen can be in interactions between fluorine, oxygen, and nitrogen. Well, why only those three? This is the sort of most extreme version of dipole-dipole interaction. It's the strongest intermolecular force when it comes to polar molecules. And so to cause that super, super strong interaction, we would need very big differences between the negative side of one molecule and the positive side of another molecule. Well, what would cause these sort of partial charges to be different? It has to do with the difference in electronegativities within the molecule itself. So fluorine being extremely high in its electronegativity can create very polar molecules. I know that this isn't fluorine, but just for theoretical, right? Oxygen also has a pretty high electronegativity. So the difference between these oxygen and hydrogen atoms creates very strong or very kind of um, all right, strong dipoles. And because those dipoles are strong, the interaction between the molecules, this intermolecular force, this dipole-dipole interaction still, but because it's in its extreme strongest form, we refer to this as hydrogen bonding. So again, pro tip, hydrogen bonding is just an extreme version of dipole-dipole interactions, but it's sort of dipole-dipole on crack, right? We can only do that when hydrogen is having fun. So hydrogen and these three elements with one another, right? Or sort of between those molecules. And again, what misconception here, hydrogen bonding, students tend to think like if a molecule has hydrogen, then it has hydrogen bonding. That's not the case. We need that extreme difference in electronegativity between hydrogen and another element to create this intermolecular attraction between molecules. Okay. We see hydrogen bonding in a lot of different places. One of the ways that we see it is in DNA molecules and DNA helicase, which actually kind of comes and unzips the nucleotides, the double helix structure. So again, why do these sort of DNA bands, like what's in the center of those the twists, right, is an actual hydrogen bonding. There's not an actual sharing of the electrons. So the DNA helicase sort of comes right down the middle and breaks these hydrogen bonds during the replication cycle. But again, when we goes back to forming the double helix structure after we finish copying the code, these hydrogen bondings are almost like magnets. They get kind of close enough together and they sort of snap back into place because of the sort of difference in electronegativities between these different molecules. So again, hydrogen bonding plays a big role in a lot of biological functions. I see this question asked a lot, not just relating to hydrogen bondings, but also in terms of sketches and illustrations. You might be asked to illustrate the proper orientation of molecules in a particular type of bond. So let's consider a molecule of ammonia over here, right? So we have the negative lone pairs of electrons that makes it really negatively charged, leaving the hydrogens in this sort of dash and wedge molecule to be positive. And so you might be asked, okay, so let's say that water is going to interact with this molecule. In what orientation or how would you draw the water molecules such that this hydrogen bond could exist, right? So we need to kind of really understand something about water molecule and it being polar, and remember that the oxygen is the negatively side part of that molecule because of the lone pairs of electrons. We would expect that the oxygen would be closest to the hydrogen such that those opposite charges can attract and yield this hydrogen bond, this interaction or attraction between molecules. What about a molecule of hydrogen fluoride? So specifically coming off of the fluorine, how would the molecule of water be aligned? What part of the water molecule would be attracted to fluorine? We need to know that in this particular bond, fluorine has the high electronegativity. It's pulling these shared electrons closer to it. So it's the more negatively side or charged part of this polar molecule. And so what would be directly opposite of the negatively side would be the positive part of water. And again, so now we would show that orientation connected to a hydrogen as opposed to the oxygen that we saw in the previous example. So this sort of common, or this is a common question of illustrating the orientation of molecules around a polar species, or like we talked about in the, I'll flip that really quickly to, you might have to draw something like this. If I give you an ion and you have to know what the charge of the ion is, I would expect you to be able to sort of draw or orient the oxygen or water molecules accordingly. Okay. All right. So those are some of the intermolecular forces that happen. We also need to talk about some of the attractions that happen sort of within a molecule that causes this. We talked about polar molecules a lot and polar ions, right? Always having those charges. Well, even non-polar molecules can have attractions to other non-polar molecules. Now that should come kind of as a rift because we talked about non-polar being symmetrical and the charges are balanced and there's sort of no positives and no negatives. All that is still true. Yet there still exist weaker but intermolecular forces between those nonpolar molecules. And we need to be able to understand kind of what causes those and why those happen. So what we know already is that the electrons are always going to be shifting around in the electron cloud. They're constantly in motion in their orbitals and things like that. And even if you kind of think about the planets as they sort of move around the sun, sometimes those planets aren't sort of always on the same side or are not always evenly distributed. So in this same scenario, the electrons are orbiting around in the cloud, and those orientations exist such that the distribution is not always symmetrical or even. Occasionally, one side of the atom can have more of the valence electrons or just electrons in general on one side than the other. And so you kind of see this sort of egg-like thing wobbling back and forth. Well, again, this is sort of supposed to represent the sort of distribution of electrons sort of in a molecule. There's sort of two nuclei here in the center, and the sort of total cloud represents around them. Well, the electrons between them and within them are constantly shifting. And occasionally we can get sort of all the electrons on one side of the molecule, making it more slightly negative just for a brief moment, right? Because these electrons are moving at the speed of light. So as soon as they're over here, they're kind of redistributed. So these are temporary shifts. That's a huge kind of thing to understand. These temporary shifts of the electrons in the cloud can create temporary dipoles. That's different than what we were talking about over here, where the difference in electronegativity was permanent, right? There's never going to be a time that fluorine's not pulling with a greater force than hydrogen. So fluorine's always going to be negative. In our scenario here, right, those temporary shifts of the electrons in clouds can create temporary partial positives and partial negatives. And then those temporary dipoles can interact with other nearby molecules. There's a lot going on here, but that's how nonpolar molecules can still also participate in these nonpolar or intermolecular forces. So we call these sort of the forces that result of these temporary shifts dispersion forces, or you might have heard the term London dispersion forces, okay? These are also referred to as van der Waal forces, as the first person who kind of understood or were studying these, the phenomenon that happens here, okay? Now, understand, dispersion forces happen in all molecules, not just nonpolar molecules. We usually don't talk about them, though, until we talk about nonpolar molecules, because the dipole forces and the intermolecular forces are much stronger, usually, than these dispersion forces. But again, understand that even polar molecules can have these dispersion forces as part of them, okay? They're the weak temporary attraction between molecules that are caused by temporary fluctuations of the electrons in the cloud. So again, here's just another illustration. Normally, we tend to think about the electrons sort of orbiting around the shell and kind of evenly. That's not always the case. Occasionally, the electrons and their sort of movements can align themselves on one side of the molecule, and that would cause this normal neutral thing to have a temporary negative charge, and the other side, which is kind of void of electrons for a moment, would be slightly positive. When that happens, right, so we can think about iodine. This is normally a nonpolar molecule, but if there's a temporary sort of gain of electrons on this side, right, so more electrons makes this ion more negatively charged, well, it has positive and negative sides too, which can interact with another iodine molecule such that the electrons on this iodine would push iodine's electrons away to the other side, and we create this positive and negative interaction. Again, briefly, right? But as soon as they sort of align, they misalign, and as soon as they misalign, they get back into their normal position. So again, these are constantly happening because electrons are always moving, but still temporary in their existence. Here's one more illustration that we tend to think about two neon atoms being noble gases and not wanting to interact. Yet there can be some interaction or attraction between the two. At the very beginning, you kind of see that the electrons, which are the blue dots within the neon sort of orbital, are sort of evenly distributed. And for the sake of this illustration, you'll notice that the electrons sort of start migrating to the bottom left side here. In doing so, watch what happens to the charges. It doesn't start off with a positive and negative. Those positive and negative charges on this neon kind of develop because of the unequal distribution of electrons. You see the void of electrons on this side. Well, notice that something is also happening here. As the electrons start to build up on sort of the bottom left half of this neon, right, what happens to the electron on the nearby neon? Notice where they go. They get pushed away, right? Because electrons and electrons are all negative, there's going to be this force of repulsion. So as the electrons start to congregate on the bottom of this molecule, they begin to push the electrons away on this neon atom. Hey, well, what does that create? A void of electrons creates a positive charge right here. And lo and behold, we have a negative and a partial positive charge. Well, the interaction between the intermolecular force between the molecules results in this weak attraction, and these neons end up being pulled a little closer together than they would normally. Okay, a lot of things going on. All right, so now this word seems to be made up, right? But it actually needs to be in your vocabulary, and I'll argue that it needs to be part of your FRQ justifications and explanations. The word is polarizability. So if you have the ability to do something, that means you're capable of doing it, but you don't necessarily flex it all the time, right? This word polarizability is the ability of molecules to become polar. And not all molecules, just like all people, don't all have the same ability. Some are better at this than other. So what would directly affect the polarizing ability of different molecules? Well, let's start with this, an analogy. Think about if you've ever sort of been on a school bus or a boat with all of your friends, right? And now one person sort of gets up and starts to kind of rock it back and forth, right? They're trying to play a joke, right? Have you ever been part of that? Well, one person by themselves may not have a significant influence on sort of the swaying motion of sort of a bus or a car or a boat, right? However, if a bunch of people sort of all kind of work together and synchronize their movements, it won't take but a few people before there's a significant shift in the object. And so what I'm trying to kind of make a connection here or parallel is the people on the boat, right, are the same as electrons in an atom. If a molecule or compound has a bunch of electrons, and they're all sort of moving around, and remember that they can temporarily align themselves, well, the size of the polar charge is going to be dependent upon the number of electrons that are participating in these shifts. In general, the more electrons that an atom has, the greater its ability to create polar sides of the molecule. Hence, the more electrons, the greater the polarizability of a particular molecule or a compound. Okay, so I mentioned the electrons. Here's another factor that can influence the polarizability. One is the nature of the bonds themselves. Kind of down here, let me show you this. We've got carbon, and that carbon would sort of be in the middle of this sort of hub. And then we have a couple of fluorines. That's these sort of dense kind of blue regions and lobes on the side, fluorine having those extra electrons. The only thing that's changing in these molecules is sort of the nature of this atom that's sort of in this big lobe that we're looking at here. And so what's happening as we sort of change from chlorine to bromine to iodine? Well, as we think about those elements and their arrangement, they're in the same group. And as we go down a group, we're adding those additional energy levels and we have a greater shielding effect. So hence, iodine has the lowest electronegativity. Chlorine has a greater electronegativity. When it compares to the bonds between C and Cl, those electronegativities are pretty similar. So we have a less polar, more nonpolar bond. Compared to the molecule over here, iodine has a very low electronegativity, very different from that of carbon. Thus, we have a more polar bond. And you can kind of see here in the illustration how the color red represents that. In general, if we have a molecule that is more polar, then the polarizability of these three molecules has changed. Hence, I would say that this molecule, the CF3I, has the greatest polarizability. It has the greatest ability to create sort of stronger interactions between molecules based on what's happening on the inside. So if kind of sequencing these, the polarizability of these three molecules is increasing. We are increasing the ability for these molecules to create stronger intermolecular forces based on the nature of the bond itself. Now, that's sometimes the question. I tend to see this kind of question more often. Both of these are nonpolar molecules. We would tend to think that they have weak intermolecular forces, right? However, the molecule CCl4 has much stronger or greater polarizability and greater intermolecular forces and greater strength between the molecules compared to CH4. Well, what would cause that? Well, each one of these chlorines, right, brings a whole lot more electrons. That's like bringing a whole bunch of friends to the boat and to the bus. And if all of these electrons can sort of shift within this molecule and shift back and forth, then we can assume, therefore, that the differences in the positive and negative regions within the molecule will become greater because there's more electrons participating. Hence, the polarizability, the ability to create a polar molecule for the CCl4 is much greater than the CH4. It has fewer electrons that can participate and kind of shift and be in different arrangements. So the intermolecular forces, the strength between sort of the attraction of different molecules for this molecule will be greater than this molecule over here. That's because it has greater total number of electrons. It's not just the valence electrons that are participating in this, it's all electrons, okay? All right. Another sort of relationship between dispersion forces and nonpolar molecules is referred to as these contact points, right? This is another example of like comparing the polarizability of nonpolar molecules. Here we have propane. in organic, the meth, eth, prop, right? Prop is a prefix that means 3 carbons. So we have a propane molecule up top, and we have a propane molecule in the bottom. In general, these are considered to be nonpolar molecules, yet there is some strength in their intermolecular forces. We'll talk more about this later, but you might know propane as the sort of gas that's in home grills and things like that. At sort of standard temperature or whatever, that propane it has relatively low interactions. In room temperature, it's a gas. We pressurize it, so if you shake the thing, it's a liquid. So don't be confused about that. But the intermolecular forces of attraction between this molecule are fairly weak. Well, why? Because if you think about kind of reaching out in connections, if I'm going to take a stick and I break it, if it's one particular stick or maybe 2 sticks, it's fairly easy for me to break because, right, there's not a whole lot of resistance in the force that I'm trying to apply. Likewise, if there are relatively few contact points between these molecules, the intermolecular attraction between these are going to be much less, right? There's sort of less space and interactions and ways in which these molecules can interact with one another. So this molecule has relatively low polarizability because of the number of hydrogens and the number of electrons that are kind of able to participate in sort of reaching out and grabbing and interacting with the neighboring molecule. I think this is octane. 1, 2, 3, 4, 5, 6, 7, 8. It is octane. Octane, right, is a molecule that's associated with gasoline. And at room temperature, you know that gasoline is a liquid. Now, it evaporates easily. That's a different ballgame. But the nature of the state of matter is that it's liquid. So why is it these have really similar structures? And this is a gas at room temperature. Propane's gas, and octane's a liquid. Well, it's because there's a greater intermolecular attraction between these two molecules. And what causes that is the sort of number of contact points, the sort of number of fingers in which this one molecule can kind of reach out and touch and interact. So again, go back to the snapping of sticks. If there's just 1 or 2, it's pretty easy. But if I have 8 or 9 sticks, I can really pull down with the same force, but it's a lot harder to sort of break those sticks and break the interactions because there's greater contact and attraction between the molecules. Again, all this is related to the dispersion forces, which goes back to the distribution of the electrons sort of shifting in the cloud. The argument I'm trying to make here is that the bigger the molecule is, the more electrons that can participate in sort of sharing the electrons. The polarizability, again, is increased or greater for this molecule compared to the smaller molecule itself. Okay, last thing. When we talk about polarizability, we can talk about something called induced dipole. When I think of the word induced, I tend to think about my kids in labor, right? So for my second kid, Anna Kate, they had to induce the labor. What that means is that they sort of had to start it a little bit earlier. They sort of gave my wife some medications that started the process or created that labor process. And that's kind of how I think about these molecules. You'll see here that this molecule is sort of just chilling. Nothing is sort of uneven about it. That would be akin or similar to a nonpolar molecule. Well, this nonpolar molecule can be influenced by othering neighboring molecules. It can be a charge can be induced on it if a neighboring thing interacts with it. So you see that we have around here some flying positive and negative ions. Every time one of these positive and negative ions gets near this neutral molecule, we create new temporary dipoles, right? And as a consequence of that, this molecule sort of changes its trajectory. We're going to talk a little bit about the influences of intermolecular forces on a bunch of different things, but right as this positive comes by, notice that the nonpolar molecule becomes partially negative and begins to sort of be attracted to it. We see it here, this negative ion here, that the positive side of that molecule sort of grabs hold of it. It's moved. So nonpolar molecules, right, we can create a temporary or induce a charge on them if we have something that's permanently polar coming by or coming near them. And so we have the charged ions on this side. Again, it doesn't have to be a charged ion. This represents a polar molecule, right? A permanent unequal distribution of the electrons can kind of come nearby a normally neutral molecule, cause it to create those charges and kind of interact with it. Okay. Here are just some examples of some of the intermolecular forces that we talked about and kind of their interactions. If I were to give you these illustrations, I would hope that you would be able to tell me what is the intermolecular force at play. And this kind of uses that flow chart at the beginning of the lesson here. But we have a couple of water molecules surrounding an ion in the middle. So this is a good example of that ion dipole intermolecular forces, like one of the 5 that we started off. We have methanol, right? A polar molecule. You can see its unevenness. And we have water, another polar molecule. What is the intermolecular force that exists between 2 polar molecules? Okay, that's dipole-dipole. However, right, is the hydrogen having fun, right? In this case, the hydrogen's attached to the oxygen, and that's the same thing here. The hydrogen is connected to the oxygen, right? FON, the hydrogen interaction here. This is an extreme difference in the difference in electronegativities, and as a result of this classifies for that hydrogen bonding interaction here, okay? Now, over here, we have a polar molecule. We have that same methanol. And over here, we have chloroform, right? CH3. Notice that the hydrogen here is connected to a carbon. And so why is this not hydrogen bonding and this is? Well, it has to do with who hydrogen is connected to. This hydrogen is not having fun. It's not connected directly to a fluorine, an oxygen, or a nitrogen. So the difference in electronegativity is not as strong here. Thus, there is some attraction between these two molecules, but it's not as strong as the bond here, right? And I say bond, notice that we're not directly sharing the electrons like a sigma bond or even like a pi bond and the attraction, but within molecules, it's really a force, a bond, a force of attraction between different molecules. So sometimes the use of that bond is kind of different or confusing because it's a different thing than what's happening within a molecule, okay? Here we can see that we have a permanently charged ion, but hexane is pretty symmetrical overall. So this is an example of an ion-induced dipole. We were talking about earlier that a normally neutral molecule can create positive and negative sides if a sort of permanently charged thing can come by and get next to it. And we see the same thing happening here, except it's not an ion creating the positive and negative part of a nonpolar molecule. Here it's a polar molecule itself. So that's a dipole-induced dipole compared to an ion-induced dipole. So some differences here, but again, this is that induced dipole that we create. Lastly, we have two nonpolar molecules that normally shouldn't be attracted to one another, but we can see that there are some black arrows that represent the dipoles that are created. And so this is a good example of, well, why is there a force of attraction? This has to do with the dispersion force, the shifting of the electrons in the cloud creating that. Here's another thing that I'll expect you to do, and you'll see this on your homework, is if I'll give you a molecule, I'll expect you to tell me what would be the strongest intermolecular force between atoms or molecules of nitrogen or between molecules of HF. Again, the chart at the beginning of this, right, the five, and asking those questions will help you get to these answers. And we'll continue to talk about this. But right now we have nitrogen. You might consider drawing the Lewis structure here. You'll see that this is a nitrogen on one side, nitrogen on the other. It's nonpolar. Well, what would be the interaction between two nonpolar substances? And that's going to be the dispersion force, the London dispersion force. That's the strongest force available, really the only force available when we have nonpolar molecules. How about H and F? Well, hydrogen and fluorine, right? Those have pretty strong difference in electronegativity. So we're talking about two polar molecules. Well, what would be the interaction between polar molecules? All right, we qualify for that dipole-dipole interaction, but then we have to ask ourselves, hey, is this an extreme version? Does this qualify for hydrogen bonding? Well, how do we know that? We would ask ourselves, is hydrogen having fun? And indeed, fluorine is one of those elements that create those extreme differences in electronegativity. So this would be hydrogen bonding. Carbon dioxide, again, this particular molecule, it would be helpful to see the Lewis structure. It's carbon in the middle, and it has two double bonds to the oxygen. So we have a linear and nonpolar molecule here. So again, this is a dispersion force because that's really the strongest and only force available for nonpolar molecules. Lewis structure for this one, again, would be helpful. We have sulfur in the middle, but we have two lone pairs of electrons connected to the two hydrogens on either side. This, because of the lone pairs of electrons in the bent Vesper geometry, is a polar molecule. So we again qualify for the dipole-dipole interactions. We ask ourselves, is hydrogen having fun? Sulfur is not one of those elements with a very high difference in electronegativity. So this is an example of the dipole-dipole interaction. So again, to get this one right, you need to know that this molecule is polar. So again, drawing Lewis structures can help. And then again, do we qualify for the hydrogen bonding based on the difference in electronegativity? Now, last one, we have sodium and we have water molecules, right? The interaction between these two, we have an ion, and we have an ion in sodium. It always has that plus charge, and we have a polar molecule, H2O, and its asymmetry. This is an example of the ion dipole force, right? The interaction between these permanently charged ions, but again, one of them is an ion, the sodium. And we talked about that earlier about how hydrogen would sort of arrange itself around the sodium. Last one, again, the Lewis structure would be important here. The nitrogen's in the middle. We have two lone pairs of electrons with three hydrogens coming off. This is another polar molecule. So it's going to default to dipole-dipole interactions. Is nitrogen having fun? It is. Nitrogen is one of those elements that qualifies for the extreme version of dipole-dipole interactions. So again, this qualifies for hydrogen bonding. All right, I'll remind you here before we sign off is that while we sort of say hydrogen bonding, right, all of these molecules also have dispersion forces at play. So if you're asked what intermolecular forces are present, you would say hydrogen bonding and dispersion forces, right? Because both exist. If it's just nonpolar molecules, though, the only intermolecular force would just be dispersion forces. All right, we'll talk more about this in class as we go. Thanks for being patient on this sort of longer video, and we'll talk more in the future. Thank you for listening.